Okay, so today the slide just summarizes the hydrostatic equations. And then I would like to emphasize the two assumptions. The first one, we always focus on the constant fluid density. So if your problem, the liquid fluid is not only one, you have several fluid in your questions. So you only can apply hydrostatic equations at the same fluid densities. Okay, and the table summarizes the two analysis methods. So usually we have the two problems. The one problem is we would like to analyze the pressures at the location 2, but you need to start from the location 1. Okay, like we have the one exercise. I just the exercise tell you the pressures at the location 1 condition, but how the location 2 pressures, like you have the pipe and the pipe inside the liquid is start to flow. So how large pressure inside the flow pipe? Okay, like these conditions. And the second condition, we call that the differential pressure analysis. So this problem is similar to our exercise. The exercise just require you answer how pressure difference between the point 1 and the point 2. Okay, so you actually follow this formula. You can observe the deflection high delta H, and you will calculate the ratio between two fluids. The gamma B is the manometer fluid, and the gamma A is the flow-in fluid. Okay, so you only need the 3 parameters, and then you can compute the pressure difference between point 1 and point 2. But in here, we use the piezometric high, the head. The formula just follow the piezometric head. And then you can see the certain definition for the piezometric head at the point 1 and the point 2. You can follow in the formula showing here. Okay, so for the hydrostatic problem, we only have 2 equations. The one equation is we have the point 1 conditions, and we would like to predict the pressure at the point 2. And we only need to remember the property is if the elevation going down and your pressure is positive increase. If the elevation going up and your pressure is negative decrease. Okay, so it's the first properties. And the second property, if you would like to measure the difference pressure between 2 points, and you only need some information like the deflection height and the specific weight ratios, and then you can quickly compute the piezometric head difference between 2 points. Okay, so because our topic here is how to measure the environment pressure, but the model in here, we have the piezoelectric material. So this is we call that the pressure transducers. That the material you can apply the pressure on the material, and the material will have some deformations. And the deformation will induce the voltage change. So you can find out the relationship between the deformations and the voltage change. And the deformation is directly related to the pressure. Okay, so the device usually will measure the voltage change and follow the formula, convert it to the voltage to the pressure. So usually we call that the pressure transducer. So this slide just a simple introduce the Tranducer's device. Okay, so you don't need to put the pipe and observe the diffraction height to convert the pressure. In the modern, right now we have the machine can directly measure the pressures, but the idea is based on the piezoelectric material properties. Okay, so and then today our very important topic is we move to the hydrostatic idea to the real case. So what about the real case? Because sometimes if we build up the reservoir or the spillway gauge, sometimes the water didn't flow. Water just stay here. And you build up some infrastructures. And sometimes the infrastructures is under the liquid. So if you design some infrastructures and there are some liquid, so you need to design the structure need to overcome the liquid weight. So as the cartoon figure showing here, we put the one plate, and the left hand side you can see there is the uniform pressure distributions. That means all of the pressures are the same, so we call that the uniform pressures. And the right hand side figure showing here, you can compute the resulted pressure force. Resulted pressure force like the arrow showing here, and then you will have the result. There is the point in here, and we call that the point is the center pressure. Okay, so we will use the CP. That means if you compute for each pressures and you compute the resulted pressure force, you need to follow integration operator in here. Each pressure need to multiply the surface area, and the N is the normal factors of the small surface area. So you can see there is the negative. You have the negative in here. That means the normal factors of a piece of the surface area is follow these directions. But your pressure is follow these directions. That's why we have the negative in here, because the normal factor of the surface area is opposite directions compared to the pressure force. Okay, and because in these problems our pressure always uniform, so didn't change with the different liquid depths. So we can take the pressure outside. So in here you can see we can take the pressure outside the integration operators. And inside we only have the normal factors and the small surface areas. And because the normal factor also always the constant factors. So this is our final result. So the pressure force for these problems is equal to the pressures multiply the total surface area. And these pressures is the magnitudes of the arrow showing here. So each pressure magnitude are the same. So we call that the uniform pressure. Okay, but in true condition, we not always have the uniform pressure. So in the following class, I will introduce another case. It's totally different in here. So the slide would like to introduce some ideas. We call that the gauge pressure rule. So what are the ideas? You have the body in here, and you can see there are some environment pressure force. You have the many environment pressure force. And the right hand side, the formula just integrate all of the pressure force, all of the pressures along the surface bodies. So you just do the integrations, and the result tell you the final pressure force is equal to 0. Okay, so if I put the bottle in here, and I can measure all of the, I can do the integrations for the pressure acting on this surface, and finally sum of the all of the pressure will equal to 0. That's the reason why usually for this kind of the problem we use the gauge pressure to analyze the pressure force problems. Because you put anything particle or material on the environment, you integrate all of the environment pressure will equal to the final resulted pressure force will equal to 0. Okay, that's why we do the pressure force analyze. Usually we use the gauge pressure unit. OK， 这个是蛮重要的，就是我们在之前做分析的时候，我们不是都用 gauge pressure 吗？那为什么要这样子？那 gauge pressure 其实就是相对于一大气压的压力。那因为一般来讲，如果自然的条件之下，它均匀的压力分布在这个物体，它最后的 pressure force 就会是0。所以如果你真的有一些 external force 的话，是你加载的，那你就是会相对于 gauge pressure， 就相对于大气压，那你施压了多少？ So that's why we always analyze the problem related to the pressure force. We use the gauge pressure. And then we call that is the gauge pressure rule. Okay? So as the figure showing here, it is a very common hydraulic engineering problems. Because we put the gauge, this is a water gauge, and then we can control the gauge to flow out some waters on the tank. Okay? And this is a normal condition. As you can see, we have the arrow, right? And this is a surface pressure force. And this is the pressure force acting on the bottom. And you see when the depth increase, okay, we have the depth increase, and then the pressure force increase. That depends on what I say, because the elevation decrease and the pressure will increase. Because the bottom need to overcome the liquid weight. So the more depth, we have the more liquid column. And then we need to overcome the liquid weight. And in that case, it is not the uniform pressure, right? And so you see the final point in here, we call that is the CP point. It is a CP point. And we have the FP pressure force. Because it is not the uniform pressure, so the pressure force is not directly equal to the pressure multiplied the total area, right? It's not. Because right now, our pressure is not the uniform pressure. So in this topic, we have two issues. The first one is, how can we compute the FP? FP is the resulted pressure force. Okay? And the second issue, where is the CP locations? Where is the CP location? What is the CP? CP is the center of the pressures. And sometimes the CP and there is the centroid point are not at the same locations. So there are some distance difference between the centroid point and the CP point. Okay? So the following is how can we determine the centroid point. Okay, centroid point usually we call that is the 行星, right? Okay, so two topic issue we have. The first one, how can we determine the FP, how large it is, and then where is the centroid and the CP points. Okay, and the idea is because we can compute, maybe I fix the point in here, and we can compute each, maybe this is pressure 1, and this is pressure 2, and then pressure 3, and the following pressures. And I can convert the pressure into the force 1, and the force 2, and the force 3. And I can compute each moment relatively to the point O. Each moment contributed from the force 1. So I can compute the force 1 multiply the L1, and the force 2 multiply the L2. What is the L? L is along the length along these directions. Okay, and then we can compute the moment for each force. And actually, you compute all of the force, and the sum of the moment will equal to the force Fp multiply the length in here. We call that is the length Cp. It's a length relative to the little point. And so the momentum will equal. So this is a very important idea. If we follow this idea, can we find out how large the Vp in here, Fp in here, and where is the Cp locations? So that's I highlight some ideas. We need to follow the momentum balance. The left-hand side, we consider the moment contributed from each force magnitude. But the right-hand side, we consider the moment from the resulted pressures, force, and acting on the Cp locations. Okay, so we need to base on this idea to find out the solution for our two issues. The first one issue I emphasize again, we need to find out the Fp magnitude, and then we need to find out the location of the Cp. Okay, so this slide just remind you how can we determine the centroid point. So basically, you just follow these formulas. We have each case in here and multiply the small areas, and we do the integrations. Okay, and finally we divided the total areas of this shape. Okay, and then we can find out the locations of the AKC. We call that is the centroid point. The centroid point is actually balance the point of all of the area. Okay, so this is just the idea to remind you how can we find out the centroid point. Okay, so this slide is very important. Right now, we try to find out the Fp and the location of the Cp based on this idea. So I put the one material inside the water. So this is I put the material in along this direction is the cross sections of this material. It's the cross sections of the material. Okay, and as you can see, where is our starting point? We pick out the 1 point in here. This is point 0. So actually, this is the yellow line is your plate. You project to the left. So actually, your target in yellow line, but you need to find out the crossover point at the little point in here. This is the point. It's a crossover point with the surface, liquid surface. Okay, and based on this 0 point, we define the y directions. So you can see there is the y directions. The y is along these directions, and these y directions, the perpendicular to the y directions along this direction, we call that the x directions. Okay, so right now the coordinate is the x along these directions. Okay, is the positive x, and the y is along these directions is the positive y directions. Okay, so in that case, we would like to find out, this is the point, is our centroid point. And this is the point, is the CP point. And how can we find out the centroid point? The centroid point is defined by the y bar in here. So the y bar is our locations for the centroid point. And the second, the YCP in here is the CP point. Okay, it's the location of the CP point. So right now our two issues, what is the FP and where is the YCP, right? Because the CP is our point location for the CP point, right? And how can we compute the FP? Okay, FP is resulted pressure force related to the pressure distributions, like the formula shown here. Okay, so we start from this formula. The formula in here. Okay, so in this integration, what is the P? You need to compute the P at the different point. Okay, so I can pick up the maybe 1 point in here. I pick out the 1 point in here. Okay, and I know that the depth along this 1 point, the depth. So I have the depth. I use the z. And you know that in that way, the length in here, this is along this direction, the y length, right? This direction is the y length. Okay, so you can convert the y to the z components. You can project the y length to find out the z depth. Okay, so I tell you the angle in here is the alpha. So actually, the P in here is equal to gamma. Gamma is the liquid specific weight. And multiply the Z, right? But we know that the Z is equal to Y sine alpha. It's equal to the Y sine alpha. Okay, we project the Y to the vertical components. So Y sine alpha is equal to the Z. Okay, so I can rewrite the formula showing here. FP is equal to, we do the integration for all small piece areas, and I put the P, I replace the P by the gamma is the liquid specific weight, Y sine alpha and the dA, right? 什么声音？ No, okay. So and then you can put some constant values outside, because we consider the liquid is the constant density. So the gamma values is always constant. And because the plate is fixed directions, so the angle alpha didn't change. So I can take outside the sine alphas. And the inside, I only have the A area integration for the total area. and the YDA, right? And if you remember the formula for the centroid point definitions, we go back to the previous slide. This is the formula when we decided the centroid point. And if you focus on the formula in here, it's similar to our current conditions. But I use the Y, right? It's an integral along the surface area, but the option right now, I use the Y. Okay, so I know that the centroid point Y bar, I define the Y bar is our centroid point coordinate, will equal to the integral along the surface area Y multiply the small piece of the area divided the total area, right? This is the centroid point definitions. And then, so we know that the resulted integral along the surface area YdA will equal to the Y bar multiply the total area. It's just based on the centroid formula definition. So we put the number, go back to the equations. So we can replace the equation, go back to here. Okay? So we know that the FP will equal to the gamma sine alpha and multiply the Y bar multiply the total area. Okay? And you can consider the parameter showing here is the Y centroid coordinate multiply the cosine alpha. That indicates the depth for the centroid point, right? So we can replace the FP, rewrite the FP is equal to gamma Z bar multiply the total area. Okay? So where is the Z bar? Z bar is equal to the centroid point may be located in here, and this is our Z bar. Okay, sorry, it's another vertical line. Okay, so if you go back to see the formula in here, so gamma Z bar actually is equal to the P bar multiply the total area. So what is the P bar? P bar is the pressures related to the depth of the centroid point. The P bar is the pressure related to the depth of the centroid point. Okay, so you can see the slides show the total final summarize. The FP is equal to the P bar multiply the total area. So for this problem, if you would like to calculate the FP, you only need to find out where is the depth for the centroid point. Where is the depth for the centroid point? And you find out the D bar. Okay? You find out the D bar, and you plot the gamma decrease, and then the total area. You can compute the resulted pressure very quickly. Okay, resulted pressure very quickly. 所以这个问题就是，不管你放了什么样的形状的物体在水中，你要去算 FP， 你只要找到这个物体的行星位置，它所在的深度，你就可以去算 FP 有多大。FP 就是所有的 pressure 的分布所换算的一个总和的压力作用长怎么样子。Okay, so the next, so we solve the first issue. first issue is what is the magnitude of the FP. So we have the second issues. How can we determine the YCP? Okay, how can we determine the YCP? So the next slide, again, we would like to decide where is the YCP locations. So as I mentioned before, we can follow the moment balance. The moment balance. So I have the FP. And maybe FP acting on these directions. So this is the FP force. Okay, I have the FP force. And I have the length. I have the length of the YCP. So actually, the 0 point in here is our rotation axis. It's rotation axis. And then we compute the YCP multiply the FP in here. That indicates the moment related to the FP. Okay? And will equal to the small force. The small force. That means indicate that each small force, and each small force will multiply the Y length. For each small force, the Y length is along these directions, so we have the Y. And then if you go into deeper part, the Y will increase. So the right hand side, the formula showing here, just the sum of the moment contribute from the DF. So the most important is, what is the DF? How can we compute the DF? DF is the small f, like the F1, F2, and if you go into deeper part, the F magnitude will increase. Okay, so the DF actually is equal to anywhere pressures multiply the small areas. And as I mentioned, the pressure, what is the pressure? The pressure is the gamma multiply the anywhere depth, right? And then we know that the Z is the gamma Y sine alpha, right? So we put or replace the P by the gamma Y and the sine alpha and the dA. So we put this equation, go back to the integration in here. So the sum integrate the Y P dA is equal to the gamma integrate the Y gamma Y sine alpha dA, right? Okay, so we replace in here, the integrate is along the total area, surface area, and you can take some constant outside the integration is the gamma and the sine alpha, and the inside we only have the Y squared dA. Y squared dA. Okay, so that's a very important item in here, the square dA. How can we compute these items? Previous slide, our integration is the integrate Y dA, and the Y dA is the relation is proportional to the centroid point coordinate. So right now, how can we compute these items? Okay. So in that way, I will write the integrate along the total area, and this is a Y squared, and the dA, I will rewrite this integration to be the Y minus the Y bar and plus the Y bar and the square dA. The right hand and the left hand, the equation are the same, right? I just minus y bar and plus the y bar again. So they are the same. Okay? And then I expand these equations. So it's equal to the sum of integrate the total surface area and y minus the y bar square dA plus 2 times the integrate A and the y minus y bar plot the y multiply the y bar and dA. And the final item is the integrate A and the y bar square dA. Okay. And I focus on this item first. So I focus on the middle items. Okay. And then so for this part I can I write in here the integrate A and the y minus y bar multiply the y bar dA is equal to the integrate A and the y bar dA minus the integrate A y bar square dA, right? Okay, so we know that some constant is the y bar. Y bar didn't change with the surface area. So I take the y bar outside. Inside, we only have integrate A y dA minus the y bar square, sum of the total area. Okay? So, as you remember for these items is equal to y bar multiply total area, right? Because based on the centroid point definitions. So we can rewrite the equation in here is the y bar multiply the y bar multiply total area. And the minus the second item is the y bar square multiply the total area. So the resulting answer in here for the integration will equal to 0, right? Because they are cancelled out. They are cancelled out. So this is the item for the yellow line I show in here. So we can go back to see the equation for this item will equal to 0. So we only, for this formula, we only have the first item. We only have the first item and the final, the third items. Okay? So, and for this item, for the first item I write down in here is the integrate the total area along the total area and the y minus the y bar square dA. What it is for these items. This item we call that the second moment of the area. The first moment is the centroid point, right? And the second moment is the y square dA integrate. But right now it's not only have the y square. We also need to minus the y bar in here. So we call that is the second moment related to the centroid point. We call that the item blue line in here is the second moment related to the centroid point. Okay, and so in this item, I just use the I bar. I use the I bar in here. Okay, and the later slide, I will tell you the I bar. If you change the different shape of your plate, the I bar will different. will be different. Because if your plate is a right angle, triangle, or elliptical, the different shape will have a different I bar values. And the third item in here is equal to the y bar square multiplied the total area. The y bar square multiplied the total area. So I go back to the equation here. So what is the right angle square value in here? So we keep the r sine alpha, but the value right now I change to multiply the I minus the y bar square a. Okay, the y bar square a. So this is our final answers, our final formulas for the right hand side in here. This is our final formula. So right now we go back to the left hand side. We go back to see the left hand side. Okay, what is the left hand side? So we move the next slide. So this is our final. For the previous slide, we focus on these items, okay? And right now we need to go back to the left, the item on the left. So we focus on these items. So as we know that what is the FP? FP we actually know is equal to the y gamma z bar multiplied the total area. And the gamma d bar is equal to the gamma d is equal to the y bar sine alpha multiply the total area, right? So we put the result showing here inside in here. So you based on this equation balance, you can cancel out some same parameters is sine alpha. That means for this problem, no matter the different alpha value, the angle is not important because the alpha angle total finally will cancel out. So it's not, the alpha in here is not important for our problems. And the second, the gamma, you can cancel out, not directly cancel out, but we now cancel out, and then you reorganize the final equations after you cancel out. So you have the YCP multiply the Y bar and then multiply the A, okay, total area. And the right hand side, we only have the I bar. I bar is the second moment related to the centroid point. And the plus the Y bar square and multiply the total area. So both sides we divided the Y bar A. So the left hand side we only have the YCP and the I bar divided the Y bar A and plus the Y bar, right? And then we know that the distance between the YCP minus the Y bar will equal to the I bar divided the Y bar A. Okay, so this is very important, the result, the final result. So we solve the second topic issue is where is the location of the YCP. It depend on the centroid point. So you need to know where is your centroid point first for your structures. And what is the second moment related to the centroid point, the I bar. And the total area is quite simple. It depends on the area of your shape. Okay? So if you put the different shape structures in here, if you put a different shape, not the plate. If the plate shape is square or elliptical, a different shape, you will have a different area and a different centroid point and a different I bar, right? So, 所以现在就是说，因为今天我们要讲比较慢，我们已经知道 FP 了，可是那 FP 作用在哪一个位置上，跟你下插到水面的这个物体的形状也有很大的关系。那当你下插到水面中的这个物体，它是椭圆形的，或是正方形，还是长方形，那你去算 I bar 就会不一样。I bar 就是这个几何形状，它的二阶举张量相对于行星在哪有多大这样子。Okay, so we already know the FP and the YCP formulas. So the next slide just show some example. If you have a different shape, how can you determine the I bar? So this slide just tell you the formula to compute the I bar. So we focus on two typical examples. The first one is a right angle plate. If you put the right angle plate into the water, where is the centroid location? So because the shape is symmetry, right? The shape is symmetry. So the centroid point is located at the center of your shape. Okay, so the centroid point in here, because the shape is a symmetry shape. And what is the I? So the formula showing here, the I for the right angle is equal to the 12 over B and H cubed. So what is the B? B is the width. B is the width of the plate. And the H is the height of the plate. But important thing in here, B is 1 power. B is 1 power. But the H is power 3. The H is the power 3. So notice that why the B is only 1 power. That's because in these problems, we assume the rotate axis is along axis. The plate rotate axis is along the axis. And the B in here is parallel to the rotated axis. So you need to identify the length, which direction of your length is parallel to the rotation axis. If your length parallel to the rotation axis, the power is 1 in here. And your length is perpendicular to the rotated axis, the power is 3 in here. So you need to identify by yourself for your problem. OK, 这里很重要，因为一般我们都背公式嘛，我们就背公式说12分之 b h 3次方。可是你怎么知道 h 要是3次方 ，b 要是1次方？你要去判断，对不对？假设都是长方形，可是长方形就有一个是长的，一个是短的那你要去判断，你在算这个4次举张量的时候，2次举张量的时候，你谁要用1次方，谁要用3次方？所以判断依据就是因为一定是有旋转才有 moment 嘛，所以判断依据是你的长度平行于旋转轴，那个是用1次方。那另外一个垂直的长度，它就是垂直于旋转轴，那个要用3次方。所以你在用这个公式，你一定要不要硬背。你可能以为永远短轴都是旋转轴，可是不一定，不一定。所以你一定要记得带这个公式的时候，先判断旋转轴是哪个方向。那垂直于旋转轴那个方向就要用3次方。Okay, so most important thing I noticed that in here is you need to identify the directions of the rotated axis and the length perpendicular to the rotated axis, you need to use the power 3. You need to use the power 3 in here. The power is 3. Okay? And then this is for another case. This is for the elliptical shape. Again, so we know that the centroid point is located at the centers. And the second moment relatively to the centroid point is equal to the 4 over pi a power 3 and the b. For this problem, you can identify the rotated axis for this problem is along the x directions. And the b parameter in here, the length also parallel to the rotated. That's why we use the 1 power in here, right? So we use the 1 power in here. And the a-axis is perpendicular to the rotated axis directions. So we use the 3 powers. So you need to keep in mind different. It depends on which one is parallel to the rotated axis. Okay, and please notice that the A and the B is the half length, not the total length. It's the half length. Okay, so not the total length. Okay, so you need to remember how to apply the formula shown in this slide. So the normal condition, we only have the 2 shape. The one shape is right angle. Another is elliptical shape. So there are some others for the circle and some triangle, and you can just take a look. But the 2 important is the right angle case and the elliptical case. You need to remember, keep in mind the formula shown here. Okay, so maybe we stop here and we have a 10 minutes break. 那这个我还是想